Okay, we'll go ahead and get started here. Okay, yeah, so welcome to Julia for Engineers, part two. My name is David Din. I am a sales engineer at JuliaHub, and today I'm going to be walking you through this little webinar we have today. And what we're going to be doing is we're going to be taking a look at how we can use Julia to model steady state and dynamic systems. All right. I have some colleagues here on the line today, so if you have questions, please shoot them into the chat or the Q&A, and either I'll address it eventually or my colleague will address it as we go. But just to let you know, everything here today will be recorded and we'll post it on YouTube and we'll send you the link for a follow-up. So if you're worried about, taking notes as fast as you can, you don't need to worry about that. The recording will be available for you, as well as all the code that we go through. All right. Okay, so what we're going to do here today, this is kind of a little agenda. I'll give a little short spiel on what the Julia system is and an overview on that. We'll talk about what, so today, we're doing part two of Julia for Engineers today. I'll quickly cover what was covered in part one. There's also a recording available for that if you'd like to watch that. Just to let you know though, watching part one, while is helpful for today, it's not absolutely necessary. And then we'll move on to solving the steady state and dynamic systems, which will be the focus of today. All right? Okay, so what is the Julia ecosystem? So with all the companies we've worked with across various industries, programs, whether it's automotive, aerospace, robotics, or AI, all these companies sort of face this two-culture problem, right? So what is that? So generally speaking, early on in the production phase, in the research and development phase, if you will, engineers and scientists, they generally prefer to use higher level succinct programming languages that allow them to perform research and analysis without having to focus on things like low level memory management and programming details, right? So basically easy language to use. So that kind of leads engineers to languages such as Python, MATLAB, and these types of ecosystems. Right, but when we move on further into the lifecycle of a program and we move on to the production phase, developers require higher performing languages that provide not only performance, but also reliability and scalability as they put these products into production. So this ultimately leads developers to languages such as C, C++, Java, and so on. All right, so what's going on here is when we move from one phase to the next, all the work, the models, the analyses that the engineers and the scientists have done in their high-level languages, all this stuff needs to be reworked for to be deployed into production. So basically, all the models and everything that was developed in the first phase has to be rewritten, reworked, and recreated for the production phase in a language that's suitable for deployment, right? So this rework of things causes a lot of friction and redundancy. So what Julia provides is an environment that is both productive enough and performant enough for developers, but at the same time is expressive and high level for engineers to use. So not only is it high level and easy to use, but it also approaches the performance of languages such as C and C++. Right? And these statements, of course, are supported by both open source and domain-specific benchmarks. On the left side right here, we have the results from the Open Source Computer Language Benchmarks program. And what this project is doing is it has a set of algorithms that need to be solved. And open source contributors will implement these various algorithms in different languages. And then the project compares the implementation of each of these languages. So we kind of look at the graph here. We see that Julia occupies the lower left-hand corner, in which the execution time of these algorithms is low in those languages, and the amount of actual code needed to implement these algorithms is also low. And then if we look at the right side right here, we have some domain-specific benchmarks. We have a rigid body system represented as a set of non-stiff ordinary differential equations. And we can see that the Julia solution, which is in Julia package, differentialequations.jl, is compared to implementations from other ecosystems, right? Fortran, Sundials, MATLAB, Dissolve, and so on. So the idea here is if we look at the Julia solution here in the green line, for any given acceptable error level along the x-axis here, we can see that the Julia solution is 1 to 2 orders of magnitude faster than the competitors in these benchmarks. And all of this information is available for you on our website for you to take a look at yourself as well. Okay, and then on top of Julia, one of the most used packages in this ecosystem is the ModelingToolkit.jl package. So this is a package that was used in part 1 and we'll be using a little bit today too in part 2. The idea is that Modeling Toolkit provides us a platform for high-performance symbolic numeric computing, right? So it's going to allow us to represent our systems and equations in form of symbols. We'll see that today. And it also has other features such as simplifying the complexity of our models so that it can be fed into the solvers, automatic differentiation, and code generation. We'll be using some macros today to simplify and reduce the amount of code we actually have to use. And of course, because Julia is a fully open source language, and so is ModelingToolkit.jl, that means anything you write with these tools or these packages will be fully composable with the open source Julia ecosystem. Okay, so while Julia and Modeling Toolkit are the sort of open source components for this modeling and simulation framework, JuliaHub is building out an ecosystem to help enable this framework and also help enable enterprises to adopt this framework. So sort of at the center of our JuliaHub's ecosystem here is what we call JuliaHub. It is built on top of Julia and ModelingToolkit.jl. So basically, you can think of JuliaSim as being built on top of open source components. And so you might be, using Julia Modeling Toolkit and thinking, hey, like there's other features that I need from this product so I can develop in an enterprise type environment. So JuliaSim provides things such as model development, including visual drag and drop GUIs and IDEs for coding. We provide AI features such as model refinement, bringing in data, combining with models, calibrating models, and discovering physics, optimization control, and creating surrogates. We also follow various model deployment standards, such as FMU generation and CI/CD. And we've also built out some model or industry-specific libraries for some of our customers. So if you're interested in learning more about JuliaSim, please reach out to us and we could have those conversations. But for today's webinar, we'll be focusing only on the open source components of this modeling and simulation framework. So we'll be focused on Julia and ModelingToolkit.jl today. Okay, so what did we go over in part 1? So if you want, we'll send out these slides at the end of the meeting, but part 1 here we have recorded. So if you follow this YouTube link, you can just basically watch my recording of when I walked everyone through part 1. What we did was we first took a look at, we solved a problem in 3 different manners. We solved 3 different problems in that part 1 webinar. So the first problem we solved was we took a look at this mass spring damper system, right? We have a mass spring damper that's attached to a wall right here. Here we have a spring, we have a damper, and then on the left side, we have a force acting on it. And we took a look at the system and we said, hey, this is the governing equation for our system. Let's go ahead and take a look at this system and solve it with using Julia code. And that's what we did. Once we did that, we moved on to saying, hey, now let's try to not just use Julia, but let's try to leverage ModelingToolkit.jl and try to solve that same equation or the same system, right? And we saw that we could use Modeling Toolkit along with its macros for code generation. And we can just specify the system very intuitively, right? Like we're kind of looking at this system here and we see, hey, there's some parameters here, a constant force, constant spring constant, a constant damping coefficient. And we can represent these as parameters as we model our system using Modeling Toolkit. And then additionally, we can say, hey, well, these are the things I'm looking for. I kind of want to know what X dot looks like and the dynamics of X maybe. So then we can specify those as variables inside of Modeling Toolkit. And then we can specify governing equations, which define how our system behaves. And we were able to solve that using Modeling Toolkit. So right here, what you see is the majority of the code that we needed to use. And we saw how easy it was to solve this in Modeling Toolkit. Then we moved on to a component-based example, which was also leveraging Modeling Toolkit, but we approached a problem from a component-based framework. So ultimately, what we wanted to do was we wanted to take a look at if we had a car that was moving along a bumpy road, we kind of wanted to see what the response was in that car, in a car that has few components, a wheel, a car, and a seat, right? So what we did in this final part was we said, hey, let's build up mass spring and damper components. We'll bring those components into one larger component, which is a mass spring damper. And then we can instantiate seats, cars, and wheels as mass spring dampers and combine this into a full suspension system and start to connect these together and understand how this car behaves as it moves over a road. All right, so that's what we did in part one. And if you're interested in learning more about this, then go ahead and watch that first recording. Okay, so what we're going to do today is we're going to take a look at a system and we're going to solve it from a steady state point of view. And then we're going to take a look at it from a dynamic point of view and solve it from there. All right. Like I said, I'll be sending out these slides afterwards. And right here, this link right here will lead you to a GitHub gist. And basically, it will lead you to this page right here. You don't have to sign in or anything. You'll be able to access this. And this contains files, which are what I'll be using today. So you basically will have the solution for today's webinar. Okay. All you got to do is follow this link right down here. Okay, great. So now let's go ahead and move on to the meat of what we're talking about here today, right? So the example problem we're going to be dealing with today is a hydraulic actuator, and we're going to be viewing it from the perspective of safety design. Okay, so what we're trying to do is we're trying to find the orifice size necessary to restrict maximum actuator speed under failure. Okay, so what we have over here is we have a hydraulic actuator on the right side. We have this actuator thing, which is this gray thing right in the middle. And this will move up and down to apply pressure to objects in this area. And the way that this actuator is controlled, it's controlled sort of by these pressures in these areas, as well as this damper that you see at the very top here. All right, so the idea is we're kind of worried that, hey, this thing under failure, this might move way too fast and crush someone's hand. So what we want to do is we want to specify a maximum allowed velocity for this actuator under failure. And then what we need to do is determine, hey, what orifice size or what hole in this little plate would allow us to achieve that maximum velocity that we specified. All right, so that's what we're going to do here. So let's go ahead and sort of move in and start examining each of these components and their physics. And then after that, we can move on to modeling it inside of code. All right, so the first physics that we're going to take a look at are the physics around the orifice plate. Remember, again, the orifice plate is right here, right? So the idea is we have a area over here, which has source pressure, which is denoted by PS. An area over here, which has return pressure denoted by PR. And then we also have this P1 and P2 sections, which have their own pressures. And the idea is that this orifice plate, the size of this plate is going to affect the relationship or the values between these pressure differentials, PS and P1 and so on. Okay, so basically we go to a manufacturer, we buy this orifice plate and place it inside of this hydraulic actuator, and we get this equation right here. Okay, so this is the delta, the change in pressure is equivalent to 1/2 rho u squared CD. All right, so what does this equation mean? So delta P is the pressure drop. So it's simply the difference in pressure between PS and P2. So PS and P1. So delta P here is just going to be PS minus P1. Rho is simply the fluid density. So that's a known equation. In this case, we're going to consider all fluid to be incompressible, so density will be constant everywhere inside of our system. U right here is the nominal fluid velocity through the orifice in terms of meters per second. So how fast the fluid is moving through this orifice. CD is the resistance coefficient for our fluid, and that is just a known value. Okay, so that's what we have, the very first equation inside our system. The second equation we have right here relates the fluid velocity, U, to the fluid flow rate, Q, right? So U is simply meters per second, and then the flow rate is in meters cubed per second. So it follows that if Q is the flow rate through the orifice plate, it follows that if you divide Q by the area inside that orifice plate, you get U, which is the speed through the orifice plate. All right. And then the final equation here is we have Q is equivalent to AX dot. All right. So Q we already talked about. That's just the flow rate, right, in terms of meters cubed per second through the orifice. We have A. A is denoted right here. You can think of it as the pressure on the actuator which P1 is acting on. All right. So A1 or A, you can think of as the area on the actuator which P1 acts on. All right. So if that is the area, it follows that the area times the velocity at which this actuator moves down must be equivalent to the flow rate that's coming in. Okay, so that's just denoted by this equation right here. All right, so now we have the three equations that kind of govern the physics around our orifice. Let's move on to the actuator. So here we have the actuator, and there are four main forces acting on this actuator. Okay, so the first force is F1. This is the force due to the P1 pressure pushing the actuator down. Okay, then we have forces from this P2 area, and that's going to be derived as F1, which is the force in that P2 area, which is pushing the actuator up. And then finally, we have FD, which is the damping force from the damper, right? And the damping force is always just going to oppose the velocity. In this case, we're taking the velocity to be going down, right? We're trying to study what the maximum velocity of this actuator crushing this hand might be. So the damping force is going to be opposing that velocity. All right. So what we're going to do is we're going to take X to be positive in the down direction, right? So down is going to be positive in this case. So we can just sum up all the forces on our actuator using Newton's law. So right here we have the equation for ma equals F, or in other words, mass times acceleration is equivalent to the sum of the forces. So on the left side, we have the mass, which is just the mass of the actuator, times x double dot, which is the acceleration of that actuator. Then we have plus F1 minus F2 minus FD. And remember, these pluses or minuses are just a result of us saying that the positive x direction is downwards. Okay, so now that we have this equation, which kind of governs the physics around our actuator, we end up with this set of equations. We just move around some variables, but we ultimately end up with these set of equations, which governs our incompressible flow system, right? So this earlier, remember, we saw this just kind of as delta P on the left side. Well, now these equations have just been set up to match up these two areas, right? So now that we have our system of equations for this incompressible flow, so what do we need to solve for? All right, so remember, we're trying to solve for the steady state scenario first, right? What we're concerned about is if this thing fails, what is the maximum velocity that this can move at? So we're saying, hey, that maximum velocity needs to be 1. We do not, under failure, we do not want this actuator moving down faster than 1 meters per second for whatever safety reason, right? So what we're going to do here is we're going to start to modify our system equations to help us solve our system. So what we have here is highlighted in red are the 4 unknowns of our system. All right, so we have U, which is the velocity of the flow through the orifice. We have A naught, which is that area in the orifice. And then we have P1 and P2, which are the pressures in these areas. Okay, and everything else is known. And then also you'll notice right here, before we had m times x double dot, or mass times acceleration on the left side of this equation, since we are solving for steady state, we can assume that the acceleration is actually 0 because we're solving for a steady state system. So we have this zeroed out on the left side. Okay, so that's it. We talked through the physics. We kind of understand what our system is. Our managers asked us to investigate this right here to ultimately figure out what A naught needs to be to achieve maximum velocity of this much. Okay, so now I'm gonna go ahead and move over to the code when we start solving this. All right, so I'm gonna, so you can do this on, let's see. Yeah, you can do this locally if you have Julia installed on your local computer. I'm going to carry this webinar out on JuliaHub. If you'd like to do it on JuliaHub, you're welcome to do that as well. You can create a free account by just going to JuliaHub.com, creating an account however you'd like. And if you create that, there will be some free usage hours for you on your free account for you to experiment inside of our JuliaHub platform. So like inside the platform, we have various applications you can use, projects that you might have. On the left side here, we'll expand the application. So if you do decide to do this on JuliaHub, I would go to the applications and open up the Julia IDE here to start coding. Basically, this is just a our instantiation of VS Code inside of our platform. All right. So I'm going to go ahead and go into my Julia IDE that I already have open over here. I'll zoom in a little bit so you can see. And I just want to reiterate that all of the code for what we're going over today is inside of this link. This link is going to be inside of the slides, right? You can just go ahead to the slides that we send out later and go to this link. But inside of this link, there's 3 files that you can use. First is the manifest file. And then if you scroll really, really far down, all the way down to here, you'll see the solution file. So this is what I'm going to be showing today. So this is the solution for what we're going to be actually going through. And at the very bottom, we have one more file, which is a project.toml file. Okay. So for those of you, so if you're not familiar, the project and manifest file are sort of what specifies the version or the package versions that you use for your code. So the idea is you can just make sure you execute all this code using the exact same versions I use today, if you want to do that. All right. So you have all this information available for you. Okay. So I'm going to go back to the Julia IDE here. And basically, I just have that part2 solution.jl file that I just showed you open here inside of my IDE. So I'm going to put this right over here so that we can see the equation a little bit. Let's see here, view. Sure. Zoom in. Okay. All right, so these are the equations that we're trying to implement and solve for, right? And remember, A naught is what we're looking for here. Okay, so here inside of my code here, I'm inside of part2 solution.jl. What I'm going to do is I'm just going to start executing this code, all right? So the packages we're going to be using here are Modeling Toolkit, Ordinary Diff EQ, and also plots. All right, so while that's loading, let's take a look. So we're going to use ModelingToolkit.jl. And what we said before is it helps us with code generation by reducing the amount of code we need to use. So the first thing we're going to do here is we're going to specify all our parameters in our system, or all our constants, if you will. And we're going to use this Modeling Toolkit macro called @parameters. And this is going to organize this whole entire variable into a format that's ingestible for solving in Modeling Toolkit. Okay, so what we're doing here is inside the parameters, we're basically just specifying all the knowns inside of our equation. So basically in our equations, everything that's black, those are all the knowns, right? So anything that's known inside of our equation, we're going to specify right here inside of our parameters. So we have x dot, which is the maximum allowed velocity for the actuator. We have A, which is not the orifice plate area, but that's the area on the actuator that the pressures act upon. C, which is the damping coefficient. We have PS and PR, which are the return and source pressures. Density, which is the density of the incompressible fluid. This C naught here is the same thing as a CD. So this is just the resistance coefficient for the fluid. And then finally, we have the mass of the actuator. Okay, So the next thing we need to do is we need to define all the variables inside of our system, right? And remember, our variables are U, A naught, P1, and P2. So those are what we need to specify inside our system. Those are what we want Modeling Toolkit to solve for us. All right. So you might notice these values next to the variables. A naught equals decimal 001 and U is equal to 100. So there's a little bit of an art to this, but these are, so what we're feeding this into is we're feeding it to a solver, right? And we're specifying initial guesses for the solver to start at. So you can think of this as us helping out the starter or the solver get to its solution. So why doesn't P1 and P2 have a guess? Like, why isn't any guess supplied here? So there's definitely going to be a little bit of an art to this, to when guesses are needed and when they are not. But in this example, our system's able to solve without knowing P1 and P2, and A naught and U are, it's not going to be able to solve without some kind of rough places to start at. Okay. And then here we have the equations which govern our system. And if you look closely, these equations are identical. All right? I'll go ahead and, yeah. So what you'll notice here that we have I'll zoom in just a little bit here so I can talk about it more easily. So you notice right here that we, like for this equation, for example, we have U tilde x dot times A over A naught. So the reason, so one thing you'll want to note when you write equations for your modeling toolkit models is that instead of using equality signs, you're going to be using these tilde signs. All right, because remember that inside of like usually an equality is an assignment type operator, and in this case we're not assigning one side to the other. Rather, we're saying, hey, in order for this model to be valid, the left side values must remain equal to the right side values, regardless of their variability. Right, so it's just keeping these equalities to be holding true rather than assigning a specific value to the left or right side. All right. Zoom out a little bit. So now that I want to go ahead and build up these variables or execute this code by doing Shift Enter. So build up my pars, build up my variables, and then build up my equation. After you do that, you need to, these are some like sort of boilerplate type code, but here we're going to use the MTK macro to help us build out a non-linear system. Remember, this is a steady state system. And we need to just simply supply the equations, variables, and parameters that we specified right up here. All right. So then after you build up that system, you can specify a non-linear problem. All you got to do is feed in that system. These two right here, we're not using, these two arguments right here, we're not going to be using. But basically, if you want to build up a system and modify any of the default variable or default parameter values up here, or modify any of the variable guesses over here, where you would do that modification is right here. But here, we're happy with the numbers I specified, so we're not going to do any modification. So we'll go ahead and execute that, and then solve the problem. Okay. Looks like the system was built up, no problem. The problem was built and the solution. Okay, great. So the return code here is success. So we successfully arrived on the solution. Okay, so how do we look at what we want to see, right? So remember, we're trying to solve for these variables. So now we can actually look at what these variables are. So here, remember that our solution is captured inside of this sole variable, right? So we can actually index into this variable to look for our values. So let's say I want to find out, hey, what was my A naught variable? Like, what did we figure out? What did we end up on? You can just go like this. You can say sole, open bracket, A naught, close bracket. And what I'm going to do is I'm going to execute this line of code. And look at that. We see that the A naught value that satisfies this entire model in the system of equations up here is decimal 0.00095. So that's the answer. That's the answer that we were looking for. We solved the system. Okay. So before we move on from this steady state part, I want to show you a few more things, but this right here is the solution. This is the answer to our problem. So like technically you are done. Okay, and all you did right there was just say, what are my parameters? What are my variables? What's my equation? And then we were able to solve it, right? So I know that, Julia and Modeling Toolkit are not the only tools available for you that you can solve this type of equation. Like I recognize that we recognize that there are other tools in industry that sort of allow you to model this type of thing and solve it. So kind of what is the difference between that and what we see right here, right? So the difference here is all of this modeling and solving, we solve all of this inside of Julia, Modeling Toolkit, and both of those are fully open source and fully like Turing complete programming languages, right? So we can go out into the open source Julia ecosystem, grab like other packages that we want to do analysis with, and it will compose fully with what you've seen here today. And that may or may not be the case with other commercial tools you're using today. Okay, so that's one big difference if you're wondering why we're doing this in Julia. Okay, so a few more things here. So similarly, we looked at the A naught value right here. You can also look at the other variables in your system. So let's say you want to know, hey, what did you end up being? We can go right here and execute this line of code. And it looks like the value of U turned out to be about 105. And there's another cool thing. So let's say, so what does this thing do right here? Right? This piece of code says, hey, go into the solution and find x dot times A over A naught. Well, if we're looking into our system, there's no variable that looks like this, right? There's no variable that looks like this at all. So like, how does it even know what to do? So the cool thing is these are symbols, and the solver or the solution knows like, hey, if I look at this value right here, it's actually the same value as U, right? Inside of our system, we've already said that these two are equalities. So when I go ahead and execute line 39 right here, it gives me the exact same value it does from line 38 because those are the same thing. Okay. And just one more thing, if if you're just like working around and you kind of want to go back into your system and say, hey, what were my parameters that I was working with? You can also index into those. So for example, if you want to see what your parameter PS was, you can just go like so and call it, right? And that makes sense. 3e to the -7. That's simply what we specified right here. This is 3e to the -7, or 3e to the 7. That's the same thing as 300 to the 5th. Okay, so one more cool thing here is, so let's say we just solved the A naught needed for a velocity of 1, right? We solved the A naught needed for a velocity of x dot is equal to 1. So what if we want to say, hey, let's go through a sweep of a few different acceptable maximum velocities, and let's plot out all the acceptable orifice areas that are associated with each of those maximum velocity values. So what we can do here is we create an empty array, which will hold our orifice area solutions. We're going to set up a second array right here. What we're doing is we're going to say, hey, we don't want to just solve for the velocity limit of 1, but we want to check out 1, 1.1, 1.2, all the way to 2. So this little array right here is going to help us do that. So this sets up an array that goes from 1 to 2 in decimal 1 increments. And then we just go through this loop right here. We go through this loop, and what we're doing is like we're saying, hey, take this problem that you set up here. The only thing I want you to change about it is instead of the default maximum velocity value, I want you to use whatever value we're using inside of this loop. So the first iteration, this will be 1. The second time this loop goes around, it'll be 1.1 and so on. So we'll solve for every single one. And what I want you to do is push my solution into this orifice array. Okay, so I'm just going to go ahead and execute this. And then now we can plot the velocity limits, which is right here, against the corresponding acceptable orifice, which is this array that we just filled out. And plot that. And there we have it. So we have, remember our first solution was a velocity of 1, and that orifice area was, I think, 0.00095. And then now we also have solutions for a sweep of acceptable velocity values. Okay, cool. So that is part one. So we just solved the entire steady state modeling system. We modeled this steady state system and solved it. We simply specified the parameters, the knowns in our equations. Then we specified the unknowns, the variables in our equations shown in red. We specified the equations, which are the physical equations which govern how our system behaves. Then we solved it with Modeling Toolkit. That simple. Okay? So let's go back to the slides here. Right, so now let's say, okay, great. We kind of figured out what the acceptable A naught is, or orifice area is, assuming we don't want the steady state velocity to exceed 1 meters per second. But let's say our manager is being extra careful, and he's like, hey, I understand that under steady state, we're not going to exceed 1 meter per second, but what about the transient response? What about when it fails and this thing isn't in steady state yet and it's moving like down really fast? Is there any chance that we exceed 1 meter per second? Because that's actually a concern, right? There's a possibility that this thing overshoots 1 meters per second and then at steady state returns to 1 meter per second. So we want to make sure that's not the case. We want to make sure that it never overshoots. All right. So we're going to move on to taking a look at the system, but solving it dynamically. So the nice thing is that we don't have to redo any of the physics. We already have our set of equations that govern our incompressible flow system. The only difference really right here is now instead of saying that A naught is an unknown, it is a known, right? Because we solved for it in the previous step already. So A naught in this case, now it is a known quantity. And what are the unknowns? Well, x dot is obviously an unknown because that's what we're trying to solve for, right? We're trying to look for the transient response of x dot. But also, we also have the acceleration back in here, right? Because now we are not solving for a steady state system anymore. It is a dynamic system, a transient response. And that follows that the acceleration will most likely be non-zero, all right? So basically, now all we have to do is kind of do a similar workflow as we just did for the steady state. But this is the system we want to solve now. Okay, so let's kind of walk through this and see what the differences are. Okay, perfect, right there. And I'll go ahead and move this right here for now. Okay, so now we're going to move on to the dynamic solution. 20 minutes left. Okay, good time. Okay, great. So the first thing we're going to do is we're going to execute this statement on line 57. Using Modeling Toolkit, T no units as T, D no units as D. What does that mean? Okay, so let's back up just a little bit. Some of you might be familiar with this already, some of you might not. But let's say I have a variable called x equal, or let's say I have a variable called x equals 1, and then another variable called, or z equals 1, and then another variable called, let's call it q is equal to 2.0. All right? So if I do this type of command, we can kind of see, hey, what type of variable is z? Well, it looks like z is an integer. Well, what type of variable is q? That's a float. That makes sense, right? We have an integer and a float here. So there's nothing weird about that, right? So let's see what t is. Type of t. Oh, that's odd. That's a number. So this right here is a type of symbol, a symbol that we can use inside of that Modeling Toolkit provides to us that we can use. Where's another example of a symbol that we use? So if you go back up here, part 1 steady state, we had this parse variable that contained all the parameters, right? So if I type in parse down here, we can see this was an 8-element vector. But look, this isn't a vector of integers. This is actually an 8-element vector of symbols, just like t is a symbol, right? So these right here, what these macros were doing previously was it not only like reducing the amount of code we need to write, but it's setting each of these items up as symbols inside of our system. All right. So just a little background on what's kind of going on there. But yeah, so basically this T and this D right here are going to be used as non as symbols. T in this case, we're going to be using to represent the time. And D in this case, we're going to be using it to represent a derivative. All right, so I'll make a little more sense as we move through. So let's go down here. So again, we're going to start to fill out our parameters, variables, and equations similar to how we did it in a steady state solution. Here we have the parameters pretty much the same as last time, but there's two differences. First, there is no x dot in here, right? X dot is no longer a known. It is a unknown. That's why it's down here in the variables. And the other difference is now we have a naught in here. So a naught is the solved value, the value that we solved for in the steady state up there. And I know there was some, this isn't accurate to significant figures, but it was like 94888 or something like that. But this is close enough for the purposes of the webinar. Okay, so those are the parameters. And then down here we have the variables. Okay, so now we are solving for a system with respect to time, right? It is no longer a nonlinear steady state type of solution. So we're going to set up our variables slightly differently right here. Okay, so the first thing you'll notice is just what the variables are. We have x, x dot, x double dot, u, p1, and p2. So the only difference from the steady state solution, so the steady state solution also had these as variables, but now the only thing we swapped out was instead of solving for a naught, we're solving for x, x dot, and x double dot, right? And you'll notice that up here, where we specify these variables, they are not a function of time, right? Because we're not solving, we were solving for steady state up here. But down here, we have our variables all as a function of t, because these will vary throughout the simulation. And so a few more differences here. So now that we're solving a dynamic system, these values that we're giving, these are no longer guesses for the system. These are initial values for the system. Okay? These are the initial values for our system. So you can kind of think of the action in the very beginning, the actuator just in its upright position and is not moving at all. And then all of a sudden, something happens, it fails, and it moves on quickly. So that's kind of what we're specifying here, right? Initially, there's no movement, and it's at its topmost position. In order to give guesses to the solver to like help it out, kind of like we did before, we simply specify it with the guess keyword right here. Okay. So now we move on down to the equations, and you'll notice that these equations right down here are just like before, they're identical to our system of equations. There's literally no difference. Yep, I'm just triple checking. Yeah, there's no difference between these equations. So we're able to like just represent them like as is. I guess I want to point this out. So some of you might notice like this Unicode text, like we have like this P sub 2. So we're able to do this kind of coding inside of Julia, right? So for example, if I want to do P sub 2, I can do P backslash underscore 2 and then press enter. So that's how you might do some cool stuff in Unicode, right? So you can like name your variables however you want. So I can do a backslash underscore o for a naught. So that's how you would do Unicode in here. So in case you're wondering, I should have specified that or mentioned that earlier. Yes, but sorry. Anyways, we were just saying that these equations are the same as these equations. So nothing, no magic there, nothing confusing there. We also have, make sure that on the left side of this equation, we have x double dot times m as opposed to 0, like our steady state equation had 0 earlier. So the new equations here are these two equations right here. So we have this dx is equivalent to x dot, and dx dot is equivalent to x double dot. So why do we need these? So remember, inside of our variables earlier, we said that, hey, x dot or x double dot, x dot, these are all variables. So we know, we as in you and me, we know that when we write these down, what these are, it's position, velocity, and time, right? We know that. But Modeling Toolkit does not know that, right? As far as it's concerned, these are just variables that we type down this way. Like it doesn't know that dot means derivative of non-dot or double dot means derivative of dot. It doesn't know that. So we need to tell it that. So that's all we're doing right here, right? We're saying the derivative of x must be equivalent to x dot. And following as follows, the derivative of x dot needs to be equivalent to x double dot. So that's all that is. All right, so now that we've done that, I'm going to go ahead and execute my parameters, my variables, and my equations. And similar to last time, we are going to set up the system to solve. But unlike last time, we're not doing a nonlinear system. We're doing a ODE system. And last time, I said that this is where you can modify your default value for your parameters and variables. That's still the case. That's still the case. But we also have this third variable right here, which is the time span over which we want our system to solve the solution. All right. So now that everything is solved, we can go ahead and plot the results. Okay. So previously we didn't do this. Like previously we didn't plot the results. We just took a look at the solution and we just indexed into it. What we did plot was we just plot these two arrays after filling these arrays out. Okay. That's what we did last time. Right now, we're actually just going to plot directly from the result. So it's pretty cool. So what we can do here is we can say, hey, I want you to plot the solution. I want you to go inside that solution and look for x. And then these are the labels I want you to give it. So I'm going to go ahead and plot this. And there you go. So here we have the position throughout our entire solution time span. And of course, the time span is right down here, and it matches up with this right here. All right, so let's go ahead and index into the one we were looking for, which is we were trying to see if the velocity right here ever exceeds 1, right? So I'll go ahead and plot line 94, and we can see that here's the transient response of the velocity for the actuator, and it does not exceed 1. So we can go back to our manager with that good news. All right, so before I move on here, just want to point out some other things about plotting. So the plot package is very useful, especially when you use it in conjunction with modeling toolkit like we're doing here. Like it really simplifies how you go into your solution and grab what you were interested in, right? So we can continue to do this. So you can plot the acceleration right here, no problem. You can also go into there and plot multiple things at once, right? So let's say I want to grab both of these variables at the same time. And then I can take a look at both the pressure. There it is, pressure P1 and P2, and it looks like the transient response, they start off at different different values, but over time, as it moves through the dynamic reaction, we see that these kind of approach nearly the same value. And the one other cool thing I want to show you is, let's say you want to see plot what the damper force is, right? So remember, inside of our set of equations, the damping force is simply the damping coefficient times the velocity of the actuator. So let's say you want to know, hey, I want to know what the damping force, how much force this damper is giving off throughout this entire simulation, right? But so the problem is, if you go into your variables right here, you'll see that, hey, there's no variable right in here that represents my damping force, right? My damping force is C times X dot, and that is not anywhere in here. So how would I plot the damping force given that I never specified it as a parameter or a variable? So as you may have guessed, so if you take a look at this is just simply C times X dot, right? Well, inside of our model, we actually do have C and we do have X dot, right? So Modeling Toolkit is smart enough to know that and look for it when we ask it to. So what we're going to do down here is, even though we don't have the damping force as a variable parameter, we can just say, hey, I want you to go look for C times X dot, right? You can just tell the solution to go look for that, and it will calculate it on its own, even though C times X dot is not a variable inside of our system. Go ahead and plot that. And there we go. So you have the damping force. Pretty cool, right? You're able to go ahead and index into these things and plot it in a very composable manner and do whatever you like. Okay, so that's our dynamic solution. Remember what we were ultimately looking for was that in the transient response, that the velocity never exceeds 1 meters per second. Okay, so that's it. So in summary, what we went over today was we went over the Julia ecosystem. We talked about, I'm just gonna go through this. I prefer to do it this way. So we talked about the Julia ecosystem, what the value proposition that Julia brings to the table compared to other programming languages available in open source and licensed industry. We talked about the various benchmarks which support our statements regarding the performance of Julia. We covered Modeling Toolkit because that's what we use both in part 1 and part 2 today. And we talked about how JuliaSim builds on ModelingToolkit.jl and enables modeling simulation for various enterprises. We took a look at part 1 recap, in which we saw, hey, looks like they solved the mass spring damper using Julia, using Modeling Toolkit, and then also using a more complex component-based modeling approach. Then today, what we did was we took look at this steady state system. We said, hey, we want to look at this system and say, what is the maximum velocity given a certain area? We derive the physics equations around the orifice. You know, this is like straightforward physics equation of activity. We derive the forces around the actuator. And then we've ended up with our incompressible flow systems in which we solve for a steady state solution and a dynamic solution. All right, so that concludes the webinar today. Appreciate everyone for joining. We will make sure to send out these slides along with a link to today's recording as a follow-up email soon. And remember, inside of these slides, you can find the link to, oh boy. You can find both the links to the first recording, which is from part 1, and you can also find the links to the solutions that we used today that I showed you in code.
Thank
All
you
right,
so much, David. This
yeah.
was great. I answered 3 questions in the Q&A section as you were discussing things. Now's a great time. If anyone has any other questions, you can plop them in there. I do think it's worth calling out a few of them. If you haven't gone and looked at the Q&A screen, I think you should be able to see the answered questions there. But very relevant question we got, David, about ways in which you can do parameter sweeps and an uncertainty estimation, which is quite relevant because David and I have been discussing that as a potential next step in this Julia for Engineers series. We've done part 1 and part 2. We don't have solid plans for part 3 yet, but we're beginning to build out the materials for that as we move forward. So please stay tuned on that. In the meantime, I put a few links in the with there so you can get started with those before we do a live demo.
Do you think I should read any of these questions out loud? Yeah, no, you're right. It's just questions regarding parameter sweeps.
Yeah, the other one was about units. If you want to take a moment there.
Oh yeah. So the question was, are we not concerned about the units of the parameters and the variables? So you were correct. Like inside of what we showed here today, we just assumed SI units, and we just basically assumed, right? But Modeling Toolkit does support specifying units, and that is something you can do, even though we didn't show it today.
Yeah, there's a great package, Unitful.jl, that allows you to attach units as a zero cost abstraction. We love those as being in the Julia ecosystem. It gives you the Unitful computations and makes sure, you know, does the unit analysis just behind the scenes for you. So it's a great technique to learn and get under your tool belt.
Okay, well, if we don't have anything else, thanks everyone for joining. Matt, thanks a lot for the support, and Sanjay for all the support. And if you have questions from us, please follow up. If not, you should be hearing from us in the form of a follow-up email in a couple of days along with the recording. So with that, I hope you all have a great weekend.
Thank you,
Goodbye.
everyone. Thanks, David.
Everyone. Thank you, David. Have a great day.